This video is brought to you by Factor. With the recent news of China producing one of the largest wind turbines yet, with a rotor diameter of 260 meters and a rating of 18 megawatts, it got me wondering why they're so big. They're almost defying imagination at this point. But bigger is always better in the world of wind. The reason is simple. We can harness more wind with bigger rotors to produce more energy. But onshore turbines have their limits. To meet these challenges, engineers have been moving offshore. However, we only have so much coast to work with, and the most powerful winds are in the open ocean, where the water is much, much deeper. What if we could push the boundaries even further? The wind industry is currently doing just that, which is why floating wind turbines are suddenly so huge. By sending these skyscraper-sized floating structures out to sea, we can take advantage of faster, more consistent wind. That still leaves some big questions though, so let's address the elephant, or maybe the turbine, in the room. Why are floating wind turbines gigantic in the first place? And can the scale of floating wind be practical to meet the planet's energy needs? Is floating wind overblown? I'm Matt Farrell. Welcome to Undecided. Despite how fantastical the concept of floating wind might seem, offshore wind turbines are going through quite the growth spurt. Earlier this year, the Danish company Vestas swept away the competition with its prototype offshore turbine, the V236 15 megawatt. A name that rolls right off the tongue. It's now the tallest turbine in the world. For comparison, here's the 300 meter or 984 foot tall Eiffel Tower, and here's the V236 turbine at 280 meters or 919 feet. These burgeoning advances come as the world grows big on big turbines, and the rationale for them all comes down to math. Before we describe how these behemoths can be buoyant, we have to establish how large these things actually are. And to help wrap your head around the size, we'll begin with the closest reference that we all have, ourselves. The average human height across the globe is roughly 5 feet 5 inches, or about 1.7 meters. A one-story building is about 4.3 meters tall. De Noord, a Dutch national monument, is the tallest traditional windmill in the world, and a restaurant, and it stands 33.3 meters. Zoom out from grinding flour to generating power, and you'll see how turbines have advanced from landscape to landmark. Since the turn of the century, US-based turbines have increased in hub height from the ground to the middle of the rotor by about 66%. And consequently, as of 2021, the average US-based wind turbine is 94 meters or 308 feet tall, or slightly above the height of the Statue of Liberty's torch. Don Quixote wouldn't have stood a chance. Now here's where it starts to kick into high gear. Maximizing wind's potential requires that we blow up the size of turbines even more. And for many countries, hitting clean energy targets also means hitting the beach. But to build turbines, not sandcastles. Now, scoring big air is easier when you have fewer obstacles in your way. Enter offshore wind, which refers to two types of tech. There's the fixed bottom turbines that you'd spot in the shallows, like the continental shelf in the North Sea, and the floating towers in waters more than 60 meters or 197 feet deep. And yes, they float, but more on how that works later. Recently, the China State Shipbuilding Corporation, or CSSC, announced it's undertaking one of the most massive turbines yet, the H260 18 megawatt. With a rotor diameter that spans 260 meters or 853 feet, its swept area comes out to 53,000 square meters, or slightly over 570,000 square feet. That's the equivalent to about 10 American football fields. And you're probably wondering, why go to such extremes? Wouldn't it be easier to station smaller, easier to handle turbines in larger groups than the other way around? Well, the answer lies in wind energy's nonlinear growth rate. You can't chart the effects of tweaking turbine measurements in a straight line. That's because slight increments cause big jumps in productivity. Mathematically, the power equation for a wind turbine shows this superlinear growth as the available mechanical power is equal to half the air density multiplied by the wind velocity cubed and the radius squared. If that's Greek to you, like it is to me, don't worry. Now, the gist of this is that as you broaden the radius of a turbine, you can generate greater factors of power. So let's use the CSSC's record-breaking rotor as an example. Now, their 2017 wind turbines started at a radius of 85.5 meters. In just 5 years, they've been able to improve the efficiencies of all the power and mechanical components, as well as increasing the radius to 130 meters, upgrading its capacity from 5 megawatts to 18 megawatts. Now, the power equation also explains the necessity of continuously elevating the turbine's height. Generally, as you head higher into the sky, the wind speeds up. The faster the wind that you're working with, the more power that you can generate. And this is especially crucial because wind velocity in the mechanical power equation is cubed. If you double the wind speed, you octuple the energy output. Now, even a tiny shift in wind speed can propel superlinear gains. A turbine spinning in a 6.7 meters per second or 15 mile per hour wind can generate twice as much energy as another that's in a 5.4 meters per second, 12 miles per hour wind. With numbers like that, setting up floating wind turbine platforms deeper into the ocean where wind speeds are generally higher starts to make more sense. But just how much more sense? Well, before I get to that, I need to talk about something else that might make a lot of sense to many of you, and it did for me. That's today's sponsor, Factor. Starting around last summer, I fell into a bad routine where I was working some crazy hours and wasn't finding the time to make myself healthy, well-rounded meals. I just didn't have the time, and it really started to impact my energy and focus. I ended up stumbling upon Factor and gave it a try, completely independent of this sponsorship. But this has been going on since last September, and, well, I love it. Eating more well-rounded meals that are chef-prepared and dietitian approved has had an impact. I feel better about what I'm eating, and they're absolutely delicious. They have over 34 weekly options to choose from, so there's always something new to try. But I've got to admit, my favorite is the Peanut Bootable. It's absolutely killer. But what's also great is that Factor offsets 100% of their delivery emissions, they source 100% renewable electricity for their production sites and offices, and have sustainably sourced seafood. No prep, no mess, never frozen, and ready in just 2 minutes. Factor is now owned by HelloFresh, and I love switching between the brands, and now you can too. Head to factor75.com or click the link below and use the code undecided50 to get 50% off your first Factor box. That's factor75.com and the code undecided50. Thanks to Factor and to all of you for supporting the channel. So back to making sense of floating wind turbines. At the world's first commercial floating wind farm, Hywind Scotland, each of its 5 Siemens turbines managed to stay stable with a tower head mass of around 350 tons, atop a spar buoy with roughly 6,060 tons of ballast, in waters that are 95 to 120 meters deep, which is about 311 to 393 feet for us Americans. And these babies surf the waves at a hub height of 98 meters or 322 feet. And these proportions sound pretty, well, quixotic. But the results are very real. When you widen a turbine's swept area, you enable it to capture more wind and generate more power. And one gargantuan turbine can do the job of many. Take the Haliade X, manufactured by the US-based company General Electric. It can provide enough energy for a UK household for 2 days with 1 rotation. I'm sure its 220-meter rotor and max height of 260 meters might have something to do with that. And to put those numbers into perspective, the largest passenger plane, the Airbus A380, flies with a wingspan of 80 meters. And offshore wind isn't just skyrocketing in size, it's shooting up in popularity as well. According to the German technology company Siemens, 2021 saw global offshore wind capacity expand by a record 18 gigawatts. That brings us to about 51 gigawatts of collective capacity in total. So why offshore? Well, location, location, location. Wind speeds are higher and more uniform off the shore than on land. On top of this, we usually like to settle down relatively close to the coast. And according to the United Nations, about 40% of people around the world live within 100 kilometers or 60 miles of the sea. In the US's case, the majority of the population is concentrated in the states that border either the ocean or the Great Lakes. As a result, almost 80% of the country's electricity demand stems from these areas. And this makes offshore wind particularly convenient because their proximity allows for shorter transmission lines. Another advantage of offshore turbines is that in the US, winds available on land tend to strengthen at night when consumer demand is low. Offshore wind projects can strategically place seaside turbines where wind speeds peak during the afternoon and evening right alongside demand. Offshore wind also helps to avoid wind shadow. That's the type of drag that reduces the speed and the amount of energy that's captured each time you add another turbine close to another one. Sailors actually have a term for this phenomenon too, called bad or dirty air. Getting caught downwind of another boat reduces your own vessel's power, slowing you down. And just as wakes trail behind boats as they zip through the water, the wakes of the turbines ripple through the air. According to the National Renewable Energy Laboratory, this can disrupt wind farm production, reducing its potential energy by about 10%. Developers on the ground do their best to circumvent this effect by spacing out the turbines, which means covering more land. But with the vast expanses of the ocean at our disposal, combined with the colossal turbine sizes that can do more work in smaller groups, offshore wind can easily steer clear of this problem. Overall, seafaring turbines have a significant edge over their land-loving counterparts, and offshore wind can certainly make for quite the catch. The US Department of Energy estimates that just 1% of offshore wind's potential could power nearly 6.5 million homes. And in a 2019 report, the International Energy Agency estimated that the technical potential of turbines deployed in less than 60 meters of water is 36,000 terawatt hours per year. That's more than enough for all of us, considering the global electricity demand is about 23,000 terawatt hours per year. But fixed bottom turbines can only go so far. Shallow water isn't distributed evenly around the world, and some locations are already fully booked or inaccessible. Beachfront property has never had a reputation for being easy to obtain. About 80% of offshore wind resources circulate in waters deeper than 60 meters anyway. For example, the west coast of the US doesn't have much of a continental shelf to work with. In California, once you go offshore, you quickly run into waters over 1,000 meters deep. The powerful wind that we want also lies above deep water off the coastlines of places like the Great Lakes, Japan, and the Mediterranean Sea. Where fixed bottom isn't feasible, floating is the way to go. And making use of these areas would be no small feat. The International Energy Agency also calculated that floating turbines could produce enough electricity for the entire world 11 times over in 2040. So how do we get there? Well, with boats. That's a major benefit of floating turbines, assembly in a port rather than out in the ocean itself. The specialized vehicles needed to install fixed bottom turbines like jack-up and dynamic positioning vessels are both expensive and hard to come by. But with floating turbines, once constructed, workers can just tow them where they need to be rather than struggle with installation on site. Boats also underpin the physics behind how turbines taller than the world's wonders can defy gravity. The same principles that make the operation of oil tankers possible apply to floating wind as well. In fact, the oil and gas industry's nautical experience is exactly what floating turbines rely on. Some iterations of floating turbines stand atop spar buoys, just like the ones that have supported offshore drilling for decades. And that's why it's no surprise that the Norwegian petroleum company Equinor founded Hywind Scotland in 2017 using its own spar buoy designs. It wasn't exactly navigating unfamiliar waters. Whether the offshore wind industry can stay afloat is another question. Like with most emerging technologies, the cost of floating wind turbines is steep. The infrastructure needed to mass produce them doesn't exist yet, and most projects are only just now getting started. According to a September 2022 White House brief, globally only 0.1 gigawatt of floating offshore wind has been deployed to date, compared with over 50 gigawatts of fixed bottom offshore wind. Advocates for floating wind argue that industrialization is key to driving down the costs. For right now though, floating wind turbines need about double the funding of fixed bottom ones. According to the National Renewable Energy Laboratory, expenses related to the turbines themselves are identical. It's the installation and increased amount of material needed for the foundations that jack up prices. The Department of Energy estimates that turbines without sea legs cost about $30 per megawatt hour, and fixed bottom wind turbines cost about $80. Meanwhile, floating wind hovers around $200 per megawatt hour. Plus, the monstrous submarine cables connected to the floating turbines aren't just far from land, they're far from cheap. As you can imagine, burying an electrical cable into the seafloor requires a boatload of insulation and meticulous engineering. I've actually touched on how astronomically expensive these networks of thick cords can get in a previous video about macro versus microgrids. Now with all that in mind, I guess you could say it's much harder for floating wind developers to keep from blowing the budget. The environmental impacts of floating turbines are another prominent concern. Oceanographers haven't yet established a concrete base of repercussions of all those concrete bases on marine ecology. We do know that offshore wind farms can act as artificial reefs that attract sea life, but whether this causes a negative ripple effect is unclear. Researchers from the US National Oceanographic and Atmospheric Administration do note that potential consequences include the introduction of noise pollution, electromagnetic fields that can disrupt the behavior of aquatic animals, and increased vessel traffic, which might mean increased vessel strikes. It's also difficult to determine how dangerous turbines are for birds in general, especially between species. The mystery won't last forever though. There are promising ways to mitigate those effects. But if one thing's for certain, it's that the theoretical possibilities offered by floating wind are nothing to blow off. The Vestas V236 15 megawatt is currently installed in the Østerild Test Center in western Jutland, Denmark. After it completes that phase, it's going to graduate to the Frederikshavn offshore wind farm in 2024. A single turbine can produce 80 gigawatt hours per year, or enough to power about 20,000 European households. If just one of these turbines can power tens of thousands of homes, then what can we achieve by moving from handfuls to hundreds? So does floating offshore wind blow you away? Or has all this turbine talk left you feeling winded? Jump in the comments and let me know. Be sure to check out my follow-up podcast, Still to be Determined. We'll be discussing some of your feedback. And thanks to all my patrons who get ad-free versions of every video. And thanks to all of you for watching and commenting. I'll see you in the next one.